main goal of the channel. One knowledge and then applying that to another task.
Nicely done. Set the bottom. Side on is first, TC, and then Nick.
When is it better to use transfer learning rather than they have to be on top? And I see second and third. Okay, what problem does meta distant transfer? We're trying to stop memorizing transferable knowledge to avoid problems of negative transfer. So that's scary. Is data is on top now. This is a true or false question. You are top now. What is the key difference between hope and L? Yeah, so both the modalities uses last layer, whereas Elmo combines multiple layers. Okay, we have release still on top. What is an assumption of transfer learning that we fail across? Yeah, that's it. That was the last question. Take QB is first place. Who's QB? Congrats. Congrats to all good players.
All right, nicely done. So there were a couple of questions on embedding structures as well. Thanks, Nura. That we covered earlier. So I guess Nura chose to also take from previous presentations as well. Okay, so a couple of things that I want to double check with you all. Again, you will have gone through the spreadsheet, and if you had coming towards the end of the semester, some people may fade out. So these, if you're involved in the preparations for the last 3 lectures, week 11, 12, and 13, for supporting structures for that, please help to double check the worksheet that you have everyone in your channel. And mention me if you find that some of your presenters or your supporters are not part, because we could have some drops and some people may not be actually on participating much. So this happens a lot during the end of the semester, as I'm sure many of you know. Okay, that said, we still want to keep up with everything, and even though today we only have 3 presenters and they're all booked, I hope we'll have a chance to discuss more to make up some of the time. But that said, we'll try to get out a little early. So while we're going through the lecture today, sprint 3 was actually due last week, but I noticed many of the teams have not put up their sprint 3 yet. So if you haven't done sprint 3, please turn that in soon. Sprint 4 is also our analysis sprint. It's due next week at week 11. The final sprint is sprint 5 due week 13, which is the same week as steps. Okay, so keep in mind for that. Okay, as part of our analysis sprint, there's basically one additional new slide which you can add to your deck. So you can just go to the sprint 4 slide deck, which is here in our channel, right? Our RAG drive. And pull out this analysis and just add this slide, copy it into your slide deck to add it. So it's important to do analysis. So the analysis means not just doing the macroscopic analysis, which would be like F1, precision, recall, etc., but actually try to look at the results coming out of your system by looking at individual outputs and then trying to craft some interesting analysis. That's usually done, as I told many of you, meso analysis. Okay, does everyone here know what meso analysis means? No? Okay, so let me describe the 3 levels of analysis that we do when we're doing machine learning NLP projects. Okay, so macro level, I think most people have heard about. These are statistics over your entire lesson, which are usually like F1 precision recall, right? We usually use this through a confusion matrix of some sort that shows on the diagonal everything that model got right, and then off the diagonal what things got wrong. Okay, or in some cases you don't have a confusion matrix if you're doing non-categorization, like you want to just generate something, then you might use metrics like blue or rouge, which are metrics from machine translation and summarization to measure against the gold standard. So those are fine. You can compare 1 or 2 different systems against that. Really, you have a baseline and implement it, or to do some A/B testing with another system to see whether things are better or worse in some way, and then you can use level information for that. Okay. Many of you have also implemented LLM as a judge to ask the LLM to judge cases, and that's usually on a Likert scale or something, and you're comparing Likert scale average outputs. Okay, so that's macro. That goes over all the items in the data set. Micro is the other extreme, right? Micro means you look at an individual data point, right? So for example, you have an output of a RAG system from an individual query and an output from a RAG system, which is a baseline. And you want to study these 2 different outputs and see whether there's any changes. Okay. Now, individual cases, you can't see many patterns, right? So when you're doing individual micro level analysis, you want to at least look through a couple different ones. Okay, these can be guided by automated metrics. So for example, like LLM as a judge, for instance, and say, oh, can you show me the one summary that's really bad, or the one summary that's the same as the baseline, or the one summary that's very different between the 2. You want to analyze what are the problems. Okay. So you can do this hopefully over a set, not too large a set. Usually their respectable size is about 10 to 30 individual examples that you and your teammates will examine. And then maybe pick one or two telling examples to put in your poster or as a result to put in. So when you read scientific papers, they often do that. They'll actually have an excerpt of some output that the system has built, and that's from their microanalysis. Everyone following those two levels first. Okay. The third one is meso analysis. And meso, as it connotes, is right in between. Right? It's not micro, it's not macro, it's somewhere in the middle. So what does that mean? Let's say you have a test data set of 1,000 documents. Okay, and what you want to do with meso analysis is not analyze the whole document set, not the whole test collection, but part of the collection that's coherent in some way. Okay, how you define coherence is up to you. Okay, you can say, oh, because it's a RAG system and I drew from Wikipedia, I'm going to just look at all the Wikipedia outputs. Okay, or I can say, oh, because the length of generation varied a lot. So if I look at the ones that are shorter, the shorter half, the 1/3 is the shortest. Okay, I want to look at whether the types of errors that I've seen are uniform across the entire data set as it is for this smaller 1/3 set. Okay, you could also say, oh, maybe I look at the queries, the results from the queries. So the queries were very short, or whether they're very detailed, whether they need multiple hops, they involve math, whether they involve multiple different sources. These are all different ways you can like chop, slice, and dice the data set. Okay, so each of these different portfolios, you can again conduct micro and macro. Okay, so usually when we do meso analysis, we say let's look at the 1/3 shortest, do macro analysis on that. Look at how the macro differs from the percentages on the entire data set. Okay, because the entire data set is telling you the entire distribution. Okay, but if you look at just let's say the 1/3 that are shorter, okay, then you might say, oh, it actually either completely hits it or completely misses it. There's no in between. Because the things are very short, right? So there's some analysis. Okay, so that will give you sort of a two distributions, a distribution of the macro over the entire data set and the distribution of statistics over the meso data set. And then trying to distill those two differences out can be very telling. Okay, that meso level analysis can be very useful for guiding you in doing further iteration and analysis that you might want to do in your last sprint. Okay, so doing the analysis now in a couple hours. I know a couple hours is very dangerous to try to get from the schedule during week 10 to 13, but you should try to do that so that you have some insight. Okay, where you see a lot of papers and a lot of people stopping is when they just do the macro analysis. Okay, and in fact, a lot of papers you read on archive, even some of them are not very repeatable. You will say they stop with percentages, like, oh, this system was statistically significantly better. Okay, so what? I don't care. I need to know what else I can do with that, right? So those statistics are useful for publishing, but they don't tell us anything useful. So don't stop with macro analysis. Yeah,
Just
John.
one point. So what about optimizations from, like, say, for meso analysis, we found exactly it doesn't really better for certain, then you're trying to tune in somewhere in pipeline optimize that.
So Jonathan asked a great question. What about optimization? If optimization helps for a particular part of the data set and not for others, then this is a great leverage opportunity, right? You can say, oh, I know it works for short, it doesn't work for long. That means I need to do what? I need to build a classification system that can differentiate, right? So the ones that are short, I'm going to send it to the case where I do the optimization. And the ones that are long, I'm not going to do the optimization. You don't get the benefit of both, right? And in fact, we saw this throughout the entire lecture series, right? There's even the first two lectures on RAG said, no, we need to know what type of resources to browse. Whether I want to directly answer, whether I want a short answer, or whether I want to triage it and do multiple rounds. We see that in models today, right? So it says, oh, I need to think for 12 seconds on the query. Why? Because some classifier looked at your query and says, that looks like a reference question, right? It's not like a pattern question. So I need to spend some time thinking. Okay, does that answer your question, Jonathan? JF, you had a question?
So okay, so for meso, you take a subset, like the short ones, you do a macro analysis. Do you also do a micro?
You can do a micro too, but usually your micro comes as part of doing your meso. So you might do some micro analysis and say, hey, I think there's something weird going on with the shorts,
Yeah.
right? So why don't I just amalgamate all the shorts together and study them as a. So my recommended profile is to do macro first, then micro, and then use the micro to guess what are useful meso. That would be my guess. Okay. Again, macro doesn't help anything. It just tells you how you're doing, right? It's like getting a B+ for your course. Okay, so I'm better than average, but I don't know what to improve on. If you never told me whether I got part A of the syllabus or part B of the syllabus, right? I just know that I'm better than average. So it doesn't help you diagnose, right? The micro helps you diagnose. You use the meso to prove that that's what you want to do. Because just looking at one test paper, for example, probably is not good enough. That's why in Singapore we have 10-year series to begin with, right? People want to do several and then they know what they're reading. Okay, does that help? Okay, so again, when you go through your analysis sprint, this is what you want to do. You want to do your macro that everyone has on their poster. You know, we did better than the other system, or we did worse, and I can tell you why we did worse, which is absolutely fine. Okay, and then the micro will tell you what might be patterns, and the meso will help you confirm these patterns. Okay, so this is what we want to do in this. That's why I said, what are the interesting aspects of your project? So it could be the optimization, it could be the error analysis that you're doing in the meso zone. Okay. We've already talked about ablations a lot. So if you have more than one knob that you've innovated with, you can turn things on and off, right? And then test those in some ways. Make sure that all the components in your system are working. And it's often good to have some very simple test cases that you're absolutely sure will work very well. So for example, you introduce something to do math very well, then you test it on some obvious easy math cases, some obvious very difficult math cases, and some non-math cases which you expect should have no difference, right? Okay. So that's all I wanted to talk about here. Okay. The other thing that I wanted to tell you about is in week 13. I'll just pull it up. Okay. In week 13, which is 2 weeks from now, I think it's we have our steps on the 19th, I think. If I'm not wrong, this should be week 13. Is that right? 12. Okay, sorry. 12 is our week 13. Yeah, today is 11, 12, 13, yeah. 12. So on the 12 is steps. It runs from around 3 o'clock to set up, but you don't have to be there at 3. It runs until about 8. 8 is the ceremony for the prizes. And right after that, I will be hosting anyone who wants to join to a session nearby and get drinks or whatever, just to hang out and talk. Okay. So I know it's week 13, people are busy, undergraduates are stressed out, but sometimes you want a beer or a soft drink or whatever. I can't be there too. We'll just hang out and have something and talk rocks about that. Okay. And then on Thursday, we have our final session. Okay. So if you'd like to join us, I'll be writing this on the general channel. I'll ask you for a poll, and then we can decide some local place to find it. Okay. Unfortunately, I don't have budget to pay for drinks, but you're welcome to buy around wherever. So I like to do that because I enjoy having these chances to talk to students in a less structured way. Okay, As usual, I wasted 20 minutes, so I can shut up now and I can let our presenters present. I can stop the screen share. And I think, Oshan, are you taking care of the first run?
Yeah, yes. Can you hear me?
Yes, I can hear you just fine. Thank you so much.
Okay. Let me
Screen share, and if you want to take it away.
share the screen.
All right. If you want to turn on your camera, you can too, but it's absolutely fine.
Okay. Uh, can everybody see my screen?
Yeah, we can see your screen now. Looks
Okay.
good.
Yeah. So in this lecture, I will be going. So we will be discussing multimodal RAG in this lecture, and I will be going through the overall overview of multimodal RAG. And so what is multimodal RAG? So we have been discussing about RAG since the start of this lecture series, and we can define multimodal RAG as an extension of RAG. It's just extends retrieval, augmentation, and generation from text to multiple modalities. So retrieval will fetch multimodal data from a multimodal database for multimodal queries. So an augmentation will accept the multimodal query and the context and generate a new multimodal query. And the generation will generate a response that is multimodal. So that is how RAG is extended. So the next question is, how is multimodality supported in multimodal RAG? So the first thing we need to discuss is what do we actually retrieve? So usually when we discuss about multimodal RAG, primarily we are referring to text, using text and images as queries. But this very recently, this has been extended to also video, audio, and also documents. And also in the database, you can find text and also multimodal data such as images, documents, audio, and video. So the survey paper, a survey of multimodal retrieval augmented generation, divides the history or the different stages of multimodal RAG into three. The first one is, and it is categorizing based on how mainly the data is stored in the database. So in the first stage, all the documents are mainly processed. So the text are extracted with OCR and all the modalities are extracted. And then all the modalities are converted to text with captioning. And these captions are stored as embeddings. And in the second phase of multimodal RAG, then we still have the extraction part. So we still get the document, extract different modalities, but now we generate embeddings in a common embedding space using multimodal encoders and sometimes model specific encoders. And the third stage is a very recent improvement, and now there are models that encode documents as screenshots. So that is the recent improvement in multimodal RAG. So these are the 3 stages identified in the survey. And the next, as we discussed what we retrieve, now the next question is how do we retrieve multiple modalities? So first here I will discuss an example that for a multimodal RAG that accepts input images and text. So the general method is you take your image and the text question and embed into a single embedding, and you do the same thing for all the data in your database, and for each pair you calculate a score and you threshold and take the context. And this is specifically for images and text. And if you take a look at how it combines image and text is using 2 encoders. In here, this paper, they are using the clip image encoder and text encoder, and then they are merging the 2 with the mean pooling. However, this survey paper asking any modality generalize the retrieval in that can be used for any modality. So we have our database D, and the documents in our database are DI. And we have our query encoded into EQ, and our encoded documents, like each DI are encoded into ZI. And we get our score, and we use our model. They use a model specific threshold in their definition, but I think this can change with the implementations. So this is a generalized formulation of multimodal retrieval. So once we retrieve, the next step is re-ranking. So in the early stages of multimodal RAG, they did not use re-ranking. But in this latest paper, they highlight why it is essential to re-rank multimodal retrieval. So the problem they highlight is multi-granularity noise correspondence problem. So let's say you are asking for a specific detail or a cropped image of a certain building, and however the information levels in text and images they vary. So incorrectly, the retriever can retrieve images that are like zoomed out than what you expected. So because the information levels in images and text are different, so re-ranking is needed here to filter out only the required images. So in the literature, they list down mainly two methods used for re-ranking multimodal RAG. And the first one is fine-tuning as a re-ranker, and they have been using MLLM multimodal large language models as re-rankers, and they are fine-tuning them to predict the relevance score. I think in the left image, I have shown the architecture they are using in a fine-tuned re-ranker, and the other method is prompting as a re-ranker. So in here, they do not fine-tune an MLLM. So you get your query, and we have our candidates from the initial retrieval, and what they do is so they concatenate our query and all the candidates and ask an MLLM to rank it basically. So and they have shown that it is very effective compared with re-ranking, but it saves a lot of computation because you didn't have to fine-tune the MLLM. So after re-ranking, the next step is augmentation. So augmentation is also important in multimodal RAG because once you have retrieved, you have data from different modalities, you have images, you have text, you may have audio and video. So we have to arrange this retrieved information before sending it to an MLLM. So I have listed 2 example structures they have used in literature. So, and the last part is after augmentation, the generation. So in a multimodal RAG, they are mainly using an MLLM for the generation. So MLLMs can be categorized into 2 parts. One is MLLMs that takes multimodal inputs but only generate text outputs. The second one is that takes multimodal inputs and also generate multimodal outputs. In this figure, I have shown the instruct blip model. So this architecture is very commonly seen in multimodal large language models that only takes multimodal inputs. So how it works is you have your text and you have your image, and an image encoder like blip will encode this into an encoding, and then you use a Q former to transform this image embedding to something that is compatible with an LLM. And this you have how they train the Q former is you have this learnable queries and you have the learnable Q former architecture, and the output of the learnable queries will be something that aligns with the LLM. So and finally you can get the answer from the LLM. And the latest versions of MLLMs are the LLMs that can also take multimodal input, multimodal data as input, and also can generate multimodal responses. And this is one of the latest models, NextGPT. And NextGPT is able to take image, audio, video as inputs and also generate each modality. Yes, and I will hand over to next.
Okay, let's thank our presenter. Okay, so we have a couple minutes to talk about this. Are there any questions so far for the overview? So who can describe as on Slack what are the differences between 1, 2, and 3 for modality multimodal RAG? Any takers? I think multimodal is pretty interesting. I mean, there's a lot of different things going on here. And so you should be at least very clear about what are the differences between 1 and 2. On Slack, I also put what the source document that Oshan mentioned says for the 3.0 version. So can anyone tell me what 1.0 means? Besides Oshan?
That means
Yeah.
for example, if you have a modality that's not text, for like an image, that would get converted to a description in text, and then that's the thing that gets embedded, and that's what represents the image.
Okay, so can we think of a corollary when we're talking about, let's say, multilingual retrieval? What would be like 1.0 for multilingual retrieval techniques?
Maybe convert everything into English.
Perfect, right? So we're doing the conversion to the most obvious single modality, right? So here we're saying text has the most signal, it's the least problematic, it's got the least number of tokens, expresses the most. So let's convert everything to text, right? And we'll do all the computations text-based. So what about modality 2.0, right? If you were to think about this cross-lingually or multilingually, what would that mean?
Multilingual embedding space.
A multilingual embedding space. So we put every token, no matter what language it's in, into this embedding space, right? So in the multimodal one, it's saying, I don't care whether you have a time series, a video, text, or images, series of images. We're just gonna throw it all into a single embedding space, and then we're querying that, right? And then we can retrieve documents for that. Then Oshan also showed you an equation, I think later in one slide, where they say if it passes a certain threshold, then we'll consider that modality for presentation, right? So look at Google AI right now, it's doing that, right? You ask the question, and then it will decide which things to show you, whether it's going to show you a location, a maps result, stock takers, a video, or shorts, or text, or websites, right? All of those things are generally being decided on. And there's a per modality threshold, as you can see in the slide that Oshan's put up again for that. Okay. Why would we need a per modality threshold? Anyone online can tell us? Why would it be helpful to have a per modalities? Come up with your own reasons or read the document. Can you guys guess? It doesn't have to be right. Why would we have a per modality threshold? So this tau on the right hand side, right? It's got a subscript M. And it's also got a subscript DI. I don't know what the DI is for here, but that's for a particular documented database, right? But let's just assume, let's say, forget the DI part, say there's a modality threshold. So meaning I need a certain similarity level for text, or another similarity level for a video, or another similarity level for a geolocation result. Why would that be?
Please.
Sorry?
Flip. You trip whatever below.
Okay, flip everything below a certain threshold. Yeah, so I would want to throw away low quality results, especially if it's like a very rare search, right? Then there's almost nothing in the collection, and I'd rather show you nothing rather than show you things that are bad. Okay, that's not the only reason though. Can you guys think of other ones that might be plausible? So Jonathan has a good point. Yeah.
I mean, one reason for like a per modality threshold could be that for a certain modality, all the vectors in the embedding space are clustered towards like one part of the space. So for the same query, one modality might be concentrated in one order of magnitude of similarity, whereas for another modality it might be totally different. So you want to account for that.
Okay, yeah. So there's are lots of considerations like that. You know, the data quality in one domain and the data quality in another modality may be quite different, right? Like you can imagine, it's pretty easy to get documents on probably any sort of thing, right? But to get videos on any sort of thing is maybe at this point in time not so easy, right? And you can imagine many queries that in geolocation you wouldn't get anything at all, right? Like unless you're searching like points of interest or restaurants, right? So then you would want to set your thresholds, right? Okay. What about modality 3.0? So modality 3.0, they said the new paradigm shift is characterized by 3 different advances in modality 3.0. Enhanced document parsing, true end-to-end multimodality, and scenario expansion. So you can read the full clip that I stole from the archive paper. But I think Oshan said that it has documents screenshots. Is that right, Oshan?
Yes.
Okay. So it's he's written on the side, it skips the extraction part. So you don't need to do any extracting. You just get the documents if you have them, and you just treat them as multimodal documents rather than thinking about text as text. If I'm reading that right.
Sorry.
Yeah.
I don't know whether this is relevant here, because just the last few days here, there was a new paper, DeepSeek, published a DeepSeek OCR. It's talking something very interesting point. It's actually, instead of extracting the text and forming the text embedding, it actually convert the text embedding to a pixel. So that save a lot of resources. Actually, I think it will result here. I don't know whether it's something similar or different topics.
I think it's very similar, right? You don't need to take the words out of the document, you just look at it. You just search directly on the representation rather than interpret it through meaning, right? Yeah, so I'm still not sure why that works very well. Has anyone read the DeepSeek OCR paper?
I do.
We might want to put it up on the channel if you guys have a chance, but also yeah, but it's good to think about why would this RAG 3.0 be a good model? I mean, it does say end to end, so the idea is that you can go from the retrieval also to the generation side, right? So you're doing from querying to retrieving to generating. So you could generate documents as output. Yeah.
The key part for the end-to-end is that if you look at the diagram, like every output is multimodal, including like text input. So you can, even if you have pure text input, you also generate like a multimodal output with like based on the diagram that we showed, which is like the key difference.
Okay. Yeah, so I encourage you to look at that as well, right? To think about how the response can also involve multimodal documents, right? And when we think about a multimodal presentation, we really haven't talked about, you know, if you are retrieving multimodal documents, how do you knit them together in a coherent response, right? Because if you think about it, in the last 15 years, you know, Google has been giving us search results as a ranked list, right? And if you think about multimodal retrieval, it's just going to give you a bunch of documents, right? But now we have AI, right? Or whatever we want to call that, right? Some type of summary of the search results. So if we're doing multimedia retrieval, we also need something like an AI mode for multimodal stuff, right? Because you're retrieving all these multimodal cosine relevant documents, how are you going to knit that together? So nicely done. Other questions?
I'm just thinking that this isn't really a question, but it's just kind of like an observation, if you will. Just thinking different modalities might have different knowledge distributions. Like for example, I think text modality would have a lot of knowledge, but maybe audio modality might not have that much knowledge being trained into the model, the pre-training stage. Yeah, so I'm just thinking how would that impact retrievals?
So some modalities are more sparse in terms of their information than others. And as Zach just posted on our discussion board, if they have time series information, that definitely figures into it, right? So you might, I think there were some queries in GPT-5 or something like that that said, tell me what's going on in the video at 31 minutes on, something like that. Or find me a picture or the clip of something happening to some object like the one that I in the video, right? There are queries like that. And the system should be able to localize and find this. So those time modalities are also very important to try to understand it and insert. So how would we want to encode that type of knowledge? How do you deal with the question that Zach has, which is like, video and speech have this additional time dimension, right? What can we do with that? I mean, for example, what is a video? A video is a collection of images, right?
Yeah.
So when we treat videos, sometimes we do it exactly like that. In fact, when we do video encoding, we often encode what are called keyframes, right? These are specific elements where the scene changes. So you really can't do differential encoding because the cut is so strong that you really need to re-encode the entire image and then start differentially encoding from there on, right? So if you have an encoding of an image and an encoding of another image, then the video is just, basically differential encoding for a couple seconds until the next keyframe comes in, right? So when we think about speech or video, often we take these types of technologies where we say we're looking at a contiguous time frame, okay, where speech is sort of uniform, like no pauses, someone is speaking in our sentence. We treat this as one utterance, we encode that frame, and then we move on, right? You can think of it that way. And these can be hierarchically too, right? So you can say video has some hierarchy, it has a couple of shots, they're composed, scene, etc. Then you can find these types of structures within a modality, especially if it's edited, right? Like if you think about the audio modality, it usually doesn't have that too much, right? But after you've composed it, it does, right? So you can think about a raw stream of speech compared to, let's say, a sitcom, right? Sitcom, you have people speaking, you have canned laughter, you have background music, and all those things help to structure out the story of a modality. Okay. All right, so let's thank our speaker again. Hello, Oshan.
Thank you, Professor.
Okay, you can stop your screen share and we'll let Yajing take over. I think Yajing is online.
Yes, I will share my screen.
Okay, yeah, when you're ready. I see Jonathan has put up the DeepSeek OCR paper, so you guys can take a look about you're sitting here. Yeah, so Shamal also says frame extraction. That's yeah, exactly what we talked about just now. Thanks for your comment.
I will try sharing again.
Yeah, we can see your screen now.
Okay, great. Let me tell my. What should I turn this video? Start video. Okay. Hello everyone. So I will continue the presentation on the multimodal RAG on by zooming into the architecture and the different methodologies that has been published.
Yajing, your microphone sounds a bit tinny, but if you don't have anything else, then that's fine.
Okay, is it better?
Not really.
Okay. I'll try with the laptop.
It's okay if we can't change over, but yeah.
Is it?
Yeah, that's better.
Is it okay? I can
Yeah, it's much better now.
Okay. Let's switch back then. Because I don't have other things, other audio devices. Okay. Yeah. So we start.
Yeah, that's much better.
So let me start with an overview of the multimodal RAG pipeline. So this is a figure from the paper from the survey. Ask in any modality, a comprehensive survey on multimodal RAG. Yeah, so we can see like there are like primarily 6 modules. The first one is on query preprocessing, which is to transform raw user queries into structured retrieval requests. And then we have the encoding multimodal encoder to convert the source data into embedding. Then after that, we have the retrieval module, which execute the retrieval process to get the most relevant information. Then we also need a fusion techniques to fuse the data from different modality to have a coherent result. Then we augment the retrieved content to the generation process, and then finally generate the answer with or without multiple modality. So I will go through each part one by one, starting with the query preprocessing. So as the figure showed just now, there are 3 key parts. First, to rewrite the query to have a complete one, by removing the ambiguous and resolve references and expand abbreviation. Also, the query also should be expanded with semantically related terms, as well as conversation history and domain knowledge, and also query dropout, which randomly remove query tokens during retrieval and serve as a regularization method. Okay. So now let's move on to the second module, which is the multimodal encoding. So so the challenges for the encoding compared to the text-only RAG is that there are the data are heterogeneous. So we need to integrate the text vectors with the other vectors from the other modality. And it could be biased on certain modality, and the language model will overly rely on especially text features. And the volume of the entire volume and dimensionality of the features from different modality could result in a very large size of data. And for encoding modules to handle multi-modal data, there are two base kind of method. The first one is to jointly encode different modality. The second one is to encode each modality first and do alignment. So for joint modality encoder, here's an example of clip. It creates a unified embedding space where different modality can be directly compared. So it jointly trained image encoder and a text encoder to predict the correct pairings of a batch of image and text. Then the text time, the length text encoder will synthesize with a zero-shot linear classifier by embedding the names of or description of the target dataset classes. And the second kind of encoding method is to do individual encoding for each modality. So here we present an example for vision, which is from called Tally. So this is kind of this is like the multimodal RAG 3.0 that we just discussed. So you will actually look at the entire document image and do an end-to-end vision encoder. By doing that, we can bypass the OCR so that we don't incur information losses. This is kind of crucial for document charts and diagrams. So after we gotten for individual for decoupled encoding, after we gotten the embedding of each modalities, we will need to align the result at token or patch level. So this is the example for that. Align number, which will do both local alignment as well as global alignment. Now let's move on to the retrieval module. For retrieval in multi-modal RAG compared to text-only RAG, we were like different modalities have its own structure and temporal characteristics. So single vector retrieval might fail to capture that effectively, and also the relevancy across different modality could be difficult to measure, and the high dimensional embedding could result in computational complexity. And there are a few, similarly, we also have few solutions addressing the problem in different ways. So first of all, we can do the retrieval using a modalities-centric retrieval. So each modality will be retrieved in the corresponding retrieval strategies, and then combine later, and during the searching, different methods has been proposed to do efficient similarity search by maximum inner product search or approximate nearest neighbor. Then after we retrieve the result, the ranking can be done by multi-stage refinement to improve the precision. Now I would like to go through like each kind of method one by one. So first one is the modality centric. Here's an example for video rec. This is kind of specific for video, for processing video, by breaking the video into chunks with OCR, ASR. It stands for automatic speech recognition, and object detection. For similarity for efficient similarity search, it can be done using these two methods. For mix, it retrieve the top 10 most similar items in the embedding space using in the product, and for ANN, it use accelerated nearest neighbor search in the high dimensional spaces. Then for re-ranking, so the initial retrieval results optimize on recall. Then we need to do a re-ranking. By re-ranking, we can refine the result by maximizing the precision. And few targeted process includes optimized example selection for in-context learning. So this can be done using multi-step retrieval, using supervised scoring with multimodal LLM for textual and visual relevance, and also like clustering-based retrieval and re-ranking. And then if we look at the relevance score evaluation in re-ranking, it can also be done using like multimodal similarity, combining various aspects or hierarchical scoring. Then there are also methods targeting at the filtering mechanism. So for example, like hard native mining to remove irrelevant or noise content before generation. Now let's move on to the next part, which is fusion. Number 4, fusion mechanisms. So the key challenges for fusion mechanism in multimodal RAG includes the integration between different modality, and the complexity of the alignment and the computation overhead when for especially attention mechanism with the increased interaction between different modality. So few solutions. First of all, score fusion and alignment. So we combine the retrieval scores from heterogeneous systems to leverage on complementary strengths, and use the shared embedding space for alignment. Also, multi-representation So I think this is not updated properly. The next two would be attention based and unified framework. I'll go directly to the stats to introduce them. So for fusion, score fusion and start with the score fusion and unified framework. It combines the retrieval scores and representation from different from multiple retrieval system for individual modalities, and then creating a cross-modal representation. So this is an example of such method. We use a clip-based score fusion. By including additional retrieval tokens in generation. Next one is fusion mechanism for using attentional-based method. So the key idea here is to dynamically modulate cross-modal interaction through attention mechanisms that allow feature from one modality to selectively attend to and to refine features from another. So this is an example of it. It combines self-attention, cross-attention, and other images in dual stream transformer to fuse the retrieved images or text in the input with input queries. And this representation obtained by the multimodal encoder will be used for VAQ vision QA classification. For fusion mechanism that has a unified framework, it consolidates multimodal inputs into coherent unified representation through projection mechanism or bottleneck architecture or format standardization that reduce dimensionality while preserving essential cross-modal information. So the example here shows like how this method in the reference convert images into text caption or complex query. So it actually separate the queries into two types. One is complex query. In this case, it will convert the images into text caption. Or for simple queries, it will overlay the text onto images, and then you will fuse the embedding while MLP length weights. Now let's move on to the last two modules of augmentation and generation. For augmentation, the challenges it comes from the cross-modal noise, like the misalignment or conflicting information across modality, semantic gaps, which refers to the semantic difference between modalities, or retrieval relevance when which refers to like to identify when and what to retrieve, especially when different modality combinations or granularity are required. The augmentation can be done in 3 ways. So first of all, to enrich the context by refining or expanding the data to provide richer and more relevant routing for generation. So an example is the image, which integrates entity relationships and semantic description into the prompt. Then for adaptive retrieval, it dynamically adjusts the retrieval strategy based on the modality requirements, content granularity, and the query complexity. So an example is the universal reg, which dynamically routes queries to appropriate corpus based on the query modality and granularity. Last but not least, iterative refinement, which refine retrieval results over multiple steps by incorporating feedback from prior iterations to ensure contextual consistency. So the last module, generation modules. So the challenge here for generation module is the coherence across modality. So we are now generating output from heterogeneous and potentially conflicting cross-modal evidence, and it might require advanced reasoning that chains across multiple modality, and also the source attribution to non-textual sources can be also challenging. So a few methods. First one is in context learning. So we leverage on the retrieved multimodal content as featured examples. And second one is to address the advanced training requirement by decompose the complex reasoning into sequential steps and integrating the evidence, multimodal evidence at each stage. For example, by generating a chain of reg or tree of reg. And last but not least, instruction tuning and preference alignment. So fine-tuning multimodal LLMs to extract specific visual features based on instructions, invoke retrieval adaptively, and balance retrieved knowledge with internal reasoning, such as extract the is leveraging on the Q former introduced earlier to extract visual features based on question instructions. That's all for the 6 different parts of the multimodal reg pipeline. Any questions?
Let's thank Yajing for her speech. Again, we have some questions that Zach put up. Fusion is a big thing for modality. So there's quite a lot of work in our information retrieval labs, some that are done in my lab as well. So I put pointers to at least one paper from my lab on fusion parts. If you're here, look into. But Zach also asked a question or two actually on this. So you should take a look. We can discuss the last one. When synthesizing and fusing multiple modalities, we often map them into a shared vector. But this blurs the what's going on, right? So if there is one event that has a logical consequence of another, that can cause problems because there could be some temporal consequences of things. How important would it be to disentangle that, and how would you do that? So first, can we decode what the question is asking? Maybe we ask Zach to clarify a bit. Zach isn't here, right? He's online. Okay, but maybe you guys can help think about this question that he asked. So if we have a question that has some time series information, I spilled the cup or something like that, and I'm taking a video of that. How do we represent that information? And how do we know whether something is causal or just or correlated? How would that make it into any of the processes that Yajing talked about, even the generation of the response and fusing the modalities together? Yeah. Okay, Indra, go ahead.
I got a possible idea for what you could do for like the entailment thing. For example, if you take the idea from like positional encoding, so like let's say like things happen in a certain sequence and you want to preserve that causality, right? So what if like you add another dimension where like that frame basically gets an encoding of like when it happened relative to other frames. And so then yeah, you can try to preserve maybe in that way.
Okay, that's a good point. So Indra is arguing for disentanglement, right? To say that no, step one happens first, then step two, we want to represent those temporally. So using other positional type of encoding methods like rope or positional encoding in the standard word vector case are useful. So in case who here has not heard of rope before? Rotational, positional encoding. So you have an encoding. It represents, it's a taking some modality and representing it as a single embedded vector, right? And rope does it by rotating the vector in a certain direction or in the space, right? So by adding an angle in a certain direction, you represent that particular embedding happens at a particular time or location. Originally, it was for a location within the document. So let's say I know the word document happens in the first position, or the word document happens in the 10th position, or it happens at the last position of the document. We want to distinguish those cases, even though it's the same. So we add a rotation of the vector to differentiate. Okay. So what Indra is saying basically is that we can do the same for information about when an event happens. So if I take an event, I encode it, and I want to say it happened at a certain time. I rotate it by a certain number of degrees, depending on when that event occurred. Okay, so that might be one way to preserve information. Okay, so that's the case where things are causal, right? As Indra said for entailment. Would we care about that if they were correlated? Would we want to disentangle things that are correlated? No answers? Anyone would like to try online? The ones of you online. There's some chats on the chat too. I'm not watching the chat. Okay, those are not relevant. I think those were for the sound quality earlier. Okay, so I think for correlation, it's not so important to disentangle them because they're both happening at the same time, but they're not causal. So you still might want to represent their entanglement as well as their disentanglement, so you can try to encode both forms. Right. Okay. Do you guys have any questions about these parts? I think there's Definitely a lot of scope for more research work. So those of you who are an undergraduate or thinking of doing graduate school, there's a lot of things that are yet to explore in these areas because it's still fairly new. It does quite take a lot of compute because, of course, you need to do the encoding. But once you've done the encoding once, doing all the subsequent post information like the rotations, the recomputation of the embeddings, etc. That's not expensive. The important part is to do the encoding part within the modality first, right? So that can be expensive, but after that, it's just regular arithmetic. It's not too expensive to me. Okay.
I did have a question
Yeah.
actually regarding the presentation. So like the part on cross attention, right? What was the attention actually like between? And there was also like one slide where there were like 3 different types of attention. So I was kind of confused, like where like yeah, what's in between actually?
So Yajing, can we see that slide that Indra is talking about? The different attention strategies. This one?
Yeah, that's the one.
Okay, so we have self-attention, cross-attention, and retrieval attention. So Yajing, can you help us understand what's going on? Yajing, you're muted. So maybe we can go look at the paper as well at the same time.
So I think the based on the maybe I can also go to so it's like for image encoder there will be self attention and cross attention between the image and text encoder, and then for retrieval attention it will be the based on the question. So there will be attention the text result with attention to the question being asked. So yeah, so the self attention should be within the modality, and then cross attention are cross modality, then retrieval attention are from the question being asked.
But across attention is across different modalities. So you have the image attending to the text attending to the image. Self-attention is image to image or text to text, even though the diagram is not quite structured right, you know, so
yeah.
Sort of implies that image is only doing self-attention, but that's not the case. And then there's the retrieval attention, which is attention between the retrieved results and then the query itself, I think, right?
Yeah.
Okay,
Just one follow-up question. Does that mean like for the image is tokenized as an image, or is it referring to the text descriptions of the?
No, the image is tokenized. So usually you run something in clip or some other type of object detector. So you have bounding boxes and you encode the bounding boxes. You have a set of tokens that represent it. I encourage you again to go through the parts and try to understand a little bit more of what's going on here. It will help you, especially the last 2 stages will help you better understand, you know, all the new technologies that are involved in GPT and AI mode at Google that help present multimodal results when they come back here. So we have our last speaker, but we're gonna take a 3-minute break. So let's thank Yajing again for her section. Okay, and Shen, you can share screen, but we'll come back in 3 minutes. So, thanks.
Can see my screen, right?
Okay, Shen, I think you can go ahead and present when you're ready.
Hi, okay. Right. So my section is on evaluation and applications. Okay. So sorry, I think I should get rid of this. I mean, there's some motivations on why you should evaluate, right? We want to reduce hallucinations. We want to make sure that there's grounded reasoning, and there's also a lot of limitations in the textual rec benchmarks that previously we have discussed, and it doesn't account for image information. So how do we evaluate, right? A lot of these benchmarks, what do we look at? Top one, top K recall. So is the ground truth among the retrieved candidates. We look at the answer accuracy and F1 scores. So there are things like exact match for multiple choice, which is in the MREC bench. And there's also freeform using like Roach L, etc., all these kind of evaluation methods. And then we also look at ablation, right? We compare the model performance when deprived of one modality. So for example, we can take out the image so it's only text only, or we can take out the text so it's image only. And then this shows what is the gain of multimodal fusion. And lastly, there's always human versus models. Okay, so I mean, there are quite a number of benchmarks. These are like 5 examples that I found, and we can just like take a quick look at what they do and how different they are and what are their focal points. Okay, so the first one, which is a MREC bench, it's just text and images. It's not really a very big size in terms of size compared to some of the others. It's around 16,000 images and about 1,000 plus multiple choice questions. And the focus is on visual centric question and answer. So next we have real MMREC, which is images, tables, and text. So these are 153 long documents, presentations, and reports. So each of them are probably something like average of more than 50 to 100 pages long. And the focus of real MMREC is on table-based retrieval, long documents, and real-world question and answer. So they have a lot of different curated question and answer pairs. VLR bench, this is images and text, so similar to MREC bench. However, it is the text is actually multilingual, and it is huge. It has more than 100,000 samples in multiple languages. So it's actually testing open-ended retrieval and vision language question and answer. Then the fourth one, we have Unidoc bench, which have PDFs that are composed of text, images, and tables, comprising over 70,000 pages and about 1,600 question and answer pairs. So it's focusing more on factual retrieval, summarization, comparison, and reasoning. And lastly, we have EMS2 Rec, which is text and images. This is actually a very huge benchmark set. It has 380,000 plus images and 540,000 text samples. So the focus is more on image captioning, multimodal question and answer, and image re-ranking, which I think Yajing has mentioned earlier. Okay, so some of like the example tasks for each of them, which we have also covered, more or less talked about in the table previously. So these are some of like the examples. This is from like MREC bench, where they give different questions and different types of images. Like for example, the example on the left is example of like perspective and angle. And the second one is more of like biological, so things like asking what happens when the strawberry goes bad. Uh, and then they find images of a strawberry which is moldy. Okay, so real MMREC bench, which we will talk about saying that they have different types of long form reports and slides. So it mainly consists of financial reports, financial slides, technical reports, and technical slides. And they ask the questions they ask are more things like how many PCI adapters can be installed in an IBM flash system. So that's why they say that the questions are tailored to be more real-world questions. And also things like retrieving data from the tables. So for example, they have a table with the financial reports and they ask specific questions that needs to be taken from the table itself. Okay, so VLR, this is kind of similar to just a visual QA, but you can notice that they are talking about, say, in this example is like Uluru, which is kind of specific to Australian context, and they also have other passages which are in different languages. Okay, so Unidoc Bench, this is a example where they pull out information from, say, journal articles, from the tables and from the images. And the last one, which is M2 Rec, so they have image captioning, they have multimodal question answering, factual verification, and image re-ranking. Okay, so I'm just gonna summarize like some of the key findings. So for MREC bench, uh, is one of the key points they make is that when you are given images, the humans actually improve a lot better than the models. So the humans improve up to 33.16%, whereas like for the models, they don't have that much improvement. And the best model in their benchmark actually is GPT-4o, and the performance is actually comparable to humans, but in both in the range of about 66 to about 80+% accuracy, depending on the different type of questions. But GPT-4 performs better in different types of questions than humans. Okay, so for real MMREC, one of the key findings they find is that actually the fusion is not very good for long documents. The models also tend to ignore visual and tabular information and usually require very specific prompting to improve the performance. So this is maybe not so surprising because we also see this kind of poor performance in just textual rec, like say when you send long documents and you tend to miss things in the middle and so on and so forth. VRR bench, so the models actually also have some struggle in selecting the relevant multimodal passages. But the positive result that they have is that for low resource languages, the multimodal context when you add visuals actually helps to improve retrieval accuracy. Okay, so for Unidoc Bench, one of their key findings and conclusion is that they said MNREC systems can offer both improved end-to-end performance and lower cost versus text-only rec. And the difficulties that they encounter are usually when you have content-rich images, and also the question type will affect difficulty. Okay, so for M2 Rec, we talked about ablation. So one of their key findings is that ablation studies show that the performance drops with removing either text or image information. So maybe to sum up just from these 5 papers, some commonalities would be that the current multimodal rec models do struggle, especially when the images are content rich with long tables and long documents. But one commonality is that even with these challenges, having multi modes actually improve performance in quite a number of contexts. Okay, I think lastly, I will talk about just a few examples of applications. I won't go very in depth. I'll just like show them. Uh, we talked about the we talked about VLR bench, so where you have tables for financial and technical documents. The other two actually have papers that I include here are actually medical applications. So the first one is MMedRec, which is actually taking the actual diagnostic images and then using a multimodal rec model to actually answer various different kind of questions. Like for example, for the chest X-ray, the example I give there is there any focal airspace opacity present? The second one that is interesting is called Alzheimer reg. But what is actually, it's not actually a diagnostic tool, but it's actually helping Alzheimer researchers to synthesize the information that has been gleaned so far from published journal articles about Alzheimer's. And so what it does is you can see from this diagram, it takes in journal articles from PubMed and then tries to do things to like summarize image captioning and then and then like encode it into a vector DB and then we can use it for retrieval for question and answers. Okay, and I think that's all I have.
Okay, so let's thank Shen Ting. Any questions for Shen Ting? Any questions from online? Okay, so in evaluation, we saw quite a number of different issues together, right? The issue of evaluating whether a modality is a relevant one, right? As well as all the key findings that Shen Ting just noted. Especially on this slide, it would be helpful for you guys to think about the times when each of these different benchmarks came out so that you can serialize them in your head, because some of these papers are older than others. And some of the difficulties with some of the findings are being resolved already. So it's also very helpful to think about within your own mind when certain things happen. Shen Ting also emphasized that some of these benchmarks are actually for visual question answering, which is not actually that RAG related, right? RAG means we are augmenting our generation with retrieved documents, which doesn't necessarily mean you're answering a question using documents themselves. So VQA is more like an IR topic. You're trying to retrieve documents to answer a question. Whereas retrieval augmented generation, as we already know, is something different. It's like using documents to help you synthesize the result. So that's why I think many of these benchmarks, they're being reused from older work in information retrieval, though they're somewhat new. The ones that specifically have a RAG component in their name are more RAG-like because there's a generative component that uses the multimodal to do the information generation rather than just retrieve. Okay, but as you can see, quite a number of them have to deal with images as text. So a lot of synthetic data, such as synthetic images like tables, charts, and plots. There's a lot of data locked up in those modalities. So having good representations of that is very much a large concern. It's a concern of our group at NUS, but also of our neighboring group at NTU. They've done quite a significant amount of research on charts and parsing and plots. So if you are in a field where there is data being generated and visualized, those systems are especially important to understand and work well, right? We've seen a couple cases in today's lecture, even in Shen Ting's work and Yajing's presentation, where they've alluded to medical documents, where captions of medical images need to have parts of it localized. For example, there's some abnormality or some area that's being competed for a score. Those things also need some careful encoding in order to get information. Okay, so one recognition of that type of image or document and then the routing of that image or document or boundary box to separate tools that can do the computation as. Okay, so I think this is also a good chance for us to think about the connection to next week. Because next week we are doing which topic? You guys remember? Graph, right? Graph rag. So if you think about this, there's a lot of cases where graph modality actually works pretty well for multimodal modalities too. Because you can say, you know, if I'm talking about a particular concept that can be represented as text, it might be also represented as an image document. It also might have a 3D model associated with it. And all of these are connected edges. So actually all of these modalities are nodes within the graph, right? So I want you to also think about when we go through next week's lecture, to think about how today's lecture, you can think about you know, the modalities as being nodes of that graph. Okay, and then how we would represent the different types of edges and the different types of nodes when we go to a graph modality. Because that's very much the methodology that we use in multimodal growth. All right, so let's thank all of our speakers again. Okay, so we look forward to next week's lecture 11, and I think we can stop here. Thanks everyone, especially for those of you online. Every one of our presenters. Nice round of applause. Okay, and that will see you next week. Get your phase 3 and phase 4 together. Thank you.